I'm going to talk about relational algorithms for the k-means clustering. I'm Kirk Pruhs. This is my co-authors are Ben Moseley, Alireza, Samadian, and Yuyan Wang. As this is sort of a new research area, I'll concentrate more on explaining the background than on our results. So here's somehow the underlying motivation for this research line. There's sort of two motivations. First is, most data, at least at the enterprise level, is stored in relational databases. And the second foundational fact is everybody wants to learn from their data. So, here's an example of, a pictorial example of a relational database. It's just a collection of tables, collection of relations where, so for example, the artist table here is a three-area relation where each of the attributes has a name here. So artist ID, artist name, and something else. All right. So here's an example of some important basic machine learning problems, and our paper is focused on one of these k-means clustering. So all of the standard machine learning problems sort of fit in the following format. There's a training phase and a prediction phase. In the training phase, the input is a bunch of points in Euclidean space, and the output is a model. In the prediction phase, later a new point is given to the model, and some prediction is made about this new point. So, a relational machine learning query is then you just want to solve whatever your machine learning problem is on your relational data. Okay, so the input is the relational data. Now, the problem with this is that there's a tight mismatch on the input here. So most of the standard machine learning problems expects the input to be, points in the geometric space, not relational data. Okay. So what's the standard way of doing this is, well, you put an intermediate stage here that converts the relational data into geometric data. And there's two parts of this conversion. One is arithmetization and one is join. So let's talk about arithmetization first. And it's just converting non-numeric data to numeric data. There's standard ways of doing this, but for the purpose, but for the moment, we're just going to abstract this away. And we'll just assume that we start with numerical data. All right, this is our standard assumption. So if you do that, then the only thing you need to do in the input conversion process is join the relational tables together. All right. Now, one disadvantage with this method is joins are computationally expensive. In the worst case, they can take, they can take time exponential in the size of the tables. All right. So necessarily, the standard approach has worst case exponential running time. All right. An alternative approach, which is what we call the relational algorithms approach, which is what we take for the k-means in this paper, is we do not do an input conversion. We design a new machine learning algorithm that accepts input directly in relational form. Okay, so we say a relational algorithm is an algorithm that accepts input in relational form and runs in polynomial time. So necessarily, if it runs in polynomial time, that necessarily definitely cannot join the tables together because that takes exponential time. So just here's sort of an analogous situation. So there's imagine that you want to do string searching on a compressed string. Okay, you sort of have a tight mismatch issue here because you want to search for some string in the uncompressed text, but you can't just apply directly a standard string searching algorithm to the compressed text. Okay. So one standard approach to doing this is you uncompress the text and then you run your standard string search. This can be inefficient because uncompressing the text may be time consuming. So there's examples of papers in the string pattern matching literature where they design new string search algorithms that work directly on the compressed data. There's no input conversion. All right. So this is analogous to our situations because one reason for storing data in relational tables is it compresses the original data. Okay. And by doing the joins, you uncompress it. All right. So we sort of wanted to do something similar where the compression comes from relational join instead of text compression. So, in some sense, this is, sort of kindred models here that we take inspiration from, are the streaming models where you only take a small number, often only one pass of the data and try to compute something. And the MPC model where the data is too large to fit in one computer. So each computer can only have some small fraction, can only see some small fraction of the data, right? But how we approach the research area of finding relational algorithms is similar to the way the research has developed in the MPC and streaming. You try to figure, what is it? We have an alternative model that, in some sense, restricts how you can access the data in some way. And now you're trying to figure out, given these restrictions, what can we still compute efficiently? All right. So our three research goals here are, develop relational algorithms for the standard machine learning problems. That's sort of maybe the applied goal. And then from a more of an algorithmic foundations perspective, we'd like to develop a toolkit of algorithmic techniques that we can use to develop relational algorithms. And we'd like to also develop a toolkit of techniques that will allow us to prove that certain problems cannot be solved by relational algorithms. Okay, so we put these together. We hope to be able to develop some understanding of which problems admit relational algorithms and which problems don't. All right. So and this paper is we sort of implement that plan in the context of k-means clustering. Okay. So here's our our strategy when we're approaching the development of k-means, of relational algorithms for k-means. Okay, we have a plan A and a plan B and a plan C. All right. So plan A is just look at a standard algorithm and see if we can find a relational implementation of the standard algorithm. Okay. A relational implementation means, you have an algorithm that's a relational algorithm and it produces exactly the same output as the standard algorithm. All right. So if you're producing exactly the same output as the standard algorithm, so then you've lost nothing by sort of requiring that your algorithm accept input in relational form. Right? Sometimes this isn't possible. If that's not possible, then plan B is we try to develop a relational algorithm that maybe produces some output that's different than the standard algorithm. But what we want is that this relational algorithm has the same theoretical guarantee that the standard algorithm is. There's some theoretical justification for the adoption of the standard algorithm, and we try to develop a relational algorithm with the same theoretical guarantee. Okay, so then to the extent that you believe that theoretical result supports the adoption of the standard algorithm, you should believe that that theoretical result should support the adoption of the relational algorithm. And plan C is if you can't get the same, if you cannot find a relational algorithm with the same theoretical guarantee as the standard algorithm, can you find a relational algorithm with some theoretical justification for that it should do well? All right, so in the paper, we sort of look at two standard algorithms that are used for k-means. One is the k-means plus algorithm. And there, you pick the centers are picked iteratively, and each point is picked as the next center with probably proportional to its distance, probably proportional to its distance to its nearest previous center. Okay. So we show in our paper that plan A succeeds for k-means plus, that we give a relational algorithm that exactly implements this k-means plus algorithm and has the same output distribution as the k-means plus algorithm. All right. And this is based on sort of two algorithmic techniques. One is rejection sampling, and one is sum product queries with axis parallel linear constraints. Then the second k-means algorithm that we look at is the standard adaptive k-means algorithm. And there we prove that plan A cannot pan out, assuming that P doesn't equal NP. Okay, by showing that producing the same output as this adaptive k-means algorithm is NP hard if the input's given to you in relational form. All right, so we can't expect to implement this algorithm. All right, but what is the theoretical justification for this algorithm? It's that it's O1 approximate. Okay, so then our goal is to try to twiddle this adaptive k-means algorithm. All right, which essentially produces weights for various points. We produce some alternate weights that are not exactly equivalent, but these weights sort of still give you the same theoretical guarantee as the adaptive k-means algorithm. It gives you O1 approximation. All right. And this algorithm is based on again on rejection sampling and on a technique that we call dynamic programming semi-rings. All right, so that's sort of an overview of our results. I got about 10 minutes left. So rather than dive into our results, I just want to, try to explain what background knowledge you would need before, you start to dive into the literature on relational algorithms, which is pretty modest at this point, at least within the algorithmics literature. I think you can get up to speed by just, just reading our paper and maybe one previous paper. All right. So, what are the things that you need to know before you can sort of start working on relational algorithms? You need to know what a join is, both the graphical and geometrical interpretation. You need to understand what a sum product query is. So that's sort of the basis for a lot of our relational algorithms. You need to understand why joins can take exponential time, why computing sum product queries can take exponential time. You need to understand what an acyclic join is, and you need to understand this algorithm called inside out for computing sum product queries on acyclic joins. All right. So I'm just going to hint at some of what these things are, just to try to convince you that this is not that difficult of background knowledge to acquire. So I'm going to define the join within two tables here, and just for simplicity, I'm going to assume that these are two tables, two column tables, and the attributes in the first table are X and Y, and the attributes in the second table are Y and Z, so they share this attribute Y. So if you look at the first row of the first table, free one, you can think of that as sort of an edge between as in a bipartite graph where the X is the X vertices of the left-hand side of the bipartite graph and the Y vertices of the right-hand side. So this table A can be thought of as this bipartite graph below with four edges. Similarly, the table B can be thought of as a bipartite graph between the Y vertices and the Z vertices. So this join can be sort of represented by this this three layer graph down below, and the join is just all the paths from X to Z there. Okay, so there are 8 paths from the X level to the Z level down there. For example, one pass is 318, and 318 is a row in the join. So the join is just all of these paths. A geometric view of this, if you think about this graph view below, let's think about those points where Y is equal to 1. Where Y is equal to 1, there are 6 paths. Okay, and they start with 3, 4, and 5, and they end with 7 and 8. And so you can think about these paths as sort of the cross product, or the projection of the points 3, 4, 5 on the x-axis and the point 7, 8 on the z-axis. You sort of project those up into the two-dimensional space. You get those 6 points. Okay. So one way to think, when you sort of form the tables, one can think about it as projecting the points down from a higher dimensional space to a lower dimensional space. And when you do the join, you project them back up from the lower dimensional space to a high dimensional space. From multiple views from multiple views within different low dimensional space, you project back up into a high dimensional space. All right, so just to try to give you a feel for what a relational algorithm is, I'm going to take a very simple problem is, find the closest point to the origin. Okay, this is a very simple version of the K nearest neighbor problem. All right. So, and we're going to do this over a particular type of join, which is a path join. Okay. So a path join is just joining together a bunch of tables where the second attribute of the previous table is equal to the first attribute of the next table. So it's a sequence of bipartite graphs. All right. And each path here from the F1 level, attribute F1 to the F5 level, is a row in the join. Okay. So good. So I want to find, I want to find the path that is closest to the origin. All right. So standard practice for doing this would be to explicitly list out all of the paths in this graph, which is, definitely could be exponential in the size of the graph. All right. So that's sort of why standard practice can take exponential time. But if you think about this for a problem like, finding the point that's closest to the origin, say in the 1 norm, is exactly the shortest path problem. Okay. So, given this graph and below that's represented by the tables above, I want to find the shortest path from the F1 level to the F5 level. Okay. So you can actually do this in roughly n log n time, using Dijkstra's algorithm or something like that. All right. So this is an example of a relational algorithm. It doesn't explicitly do the joins, but it still solves the problem. All right. Yeah. Okay. So. All right, and one way to think about the shortest path problem is you want to take the minimum overall rows or the minimum overall paths of the sum of the costs over the edges. Okay, so this is one can express shortest path as a min sum problem. What is it that makes what is the underlying fact about these arithmetic operations that make Dijkstra's works? Well, you really use the fact that min plus is the commutative semi-ring, where plus is the multiplication operator and the addition operator is min. Okay, so in particular, plus distributes over min. And that's really what you use. So one can generalize this. So any sort of sum product query over a commutative semi-ring can be computed on a path join using Dijkstra's algorithm. All right, so here's one problem that you run into if you try to generalize this, is that it's NP hard to compute, even decide whether the join of your tables are is empty or not. Okay, and there's this there's a simple reduction from 3-sat to show that. So this is the problem, but these sort of tables just never arise in practice. I mean, these tables are designed by a human usually, so you would never have these sort of tables. So we need to sort of get around this fact that we don't want to sort of abstract away the fact that these tables can be complex. So, one way to do this is just assume that tables do not have a complex structure. Okay, and the most standard way of doing this is assuming that the tables are acyclic, which I'm not going to bother to define, but it's a notion of acyclic that generate that it's a hypergraph notion of acyclicness that generates the standard graph. It generalizes the standard graph notion of acyclicness, and some product queries can be computed efficiently by a relational algorithm for acyclic tables. All right, and the algorithm that does that is essentially a generalization of Dijkstra's algorithm to compute minimum cost objects that are not paths. They're sort of more general than that. But one way to, another way to think about the definition of acyclicness, it's sort of the structure that you need in order that you can generalize Dijkstra's algorithm. All right. So that was pretty quick, but this is like, these are the things that the background knowledge that one needs to start working in the relational algorithms area. And I probably should have put this up earlier, but somehow the takeaway points here is that the barrier to entry to start developing relational algorithms is relatively low. There's a small, modest amount of knowledge that you need from the database literature, and there's a couple papers in the algorithmic literature. I think the area is interesting. Presumably, there's some low-hanging fruit out there. It's not a well-researched area. So I appreciate you listening. Thank you.